So the lemma established a connection between max min of a player, in this case the second player, and min max of the first player. And basically what it says is that the optimal that the second player can guarantee to itself is the opposite of the worst that it can inflict upon the other player. And again, that's quite intuitive given that zero something. So formally it means that if we have a constant sum game and the total sum is always constant c, then max over s2 min over s1, so max over y's min over x's of u2 is s minus min over y's max over x's of u1. And moreover, the values that allow for those maxima, max min and min max, they are the same. So the set of argmax, those y's that allow for those values, they're the same. And as I said, intuitively, it means that the best I can do to myself, I can guarantee, not necessarily always do, but guarantee for myself, is the worst I can guarantee to inflict upon the other player. So let us prove that theorem. We use the fact that for any function, finding the minimum value of that function, finding the minimum value of minus function is exactly the same as the minus of the maximum of the function. So we need to basically apply minimum twice. First, that the extremum values, they are the same, up to that you need to minimize the minimum of the function, then it's the same as maximizing the function. But to get the same value, of course, you need also to add another minimum. And the values of these extremum, of the minimum minus and the maximum of the function, the values that allow that, so the values in the domain, the z values that allow that, are also the same. And applying this rule to the function u2xy as a function of x means that for each y, the minimum over s1, minimum over x's, is equal to the maximum over x's of minus y2, minus u2. Now, since minus u2 is u1 minus s, we can just replace the maximum of minus u2 by maximum of u1 minus x. And then we apply this first rule for maximizing or minimizing the new function again upon the new function as a function of y. And here we get that the maximum over y of minimum of u2, which in the wait a second, yes, exactly, that applying that rule, we get that this maximum, it's minimum over y of minus minimum of u2. Exactly that we have two minima and then the equality hold. And then we just use that we know that we have proved that the minus minimum of u2 is equal to maximum of u1 minus s. Of course, the constant does not matter, so that's why maybe people just study zero-sum games, because constant simply adds something to right. Okay, so eventually, having played with that rule, we have proven the lemma. We apply this rule twice, and also the maximizers and the minimizers are the same too. In that rule. So that's why we also have that the y's that maximize that expression, maximum y over the minimum of x of u2, are exactly those who minimize the maximum over uy. Okay, so that is the connection between max min of u2 and min max of u1. And that's an interesting lemma for its own right, but of course we are now going to use it for the really interesting theorem. And that is something which allows us to basically connect, which shows why, in general, Nash equilibria are very interesting, beautiful, and simple, I would say, in zero-sum games. And we can connect the definition of max minimizers of constant sum games. Well, they're defined in general, but we can connect them to the equilibria in the case of constant sum games. So, given a constant sum game, where the constant, which is C, the following statements hold. So first, if x star y star is an equilibrium, then x is a max minimizer for player 1 and y is a max minimizer for player 2. So if it's an equilibrium, then both strategies have to be the safety strategy, so to speak, the best I can ensure for myself, for both players. They both have to play safety strategies. The second statement is that if it's an equilibrium, then the min maximum over S1 and maximum over X, minimum over Y of U1 is the same as minimum over Y and maximum over S of U1. So the order of max min does not matter, whom basically I can maximize X, minimize Y in that order, or maximize first. Let's look. I can first minimize Y and then maximize S, or first maximize S and then minimize Y. The value will be the same, which is generally not the case. Generally, there is only one direction, which is always true. And moreover, that value is exactly the value of the first player in this equilibrium. We assume it's an equilibrium. So that's another conclusion from being an equilibrium. And that also implies, of course, that all Nash equilibria have the same utilities, because the utility of the first player is given by this expression, max min, or min max. And the utility of the second player, as always, of course, is simply the C minus the first player. And then we have the opposite direction. So if that max min equals to min max, for example, we've already proved, hopefully we will prove that that is fulfilled by an equilibrium. And if x prime is a max min for player 1 and x star and y star is a max min for player 2, then that couple is Nash equilibrium. So, and Nash equilibrium implies that equality, max min equals min max, and that each of the strategies is a max minimizer of the corresponding player. But now we also say that the opposite also is true. If we both know that max min equals min max, and that we have a max minimizer for player 1 and max minimizer for player 2, then the couple is a Nash equilibrium. And now let us prove. First we prove that assuming the x star y star is Nash equilibrium, we have those implications, 1 and 2. So first, since it's a Nash equilibrium, then for any y, of course, it's better to use x star y star than x star y, because y star is the best response to y star, to x star. Now, since that was for y2. For utility of, I said y, u2, for the utility of the second player. I sometimes probably confuse u and y. Y is the variable and u is the utility function. Since we have that the utility of the second player is greater or equal to the utility of the second player in x star y, then for the utilities of the first player in the same profiles, we're going to have the opposite inequality. And since the utility of the first player in x star y star is not greater than its utility in x star y for any y, then we can say that it's equal to the minimum such utility. It's because for when y is equal to y star, it's equal, and it's always not greater. So when y equals to y star, then that is simply the same expression. And since for each y, the utility of the first player in x star y star is at most its utility in x star y, then it's equal to the minimum. And of course, we now can also maximize over all the possible x's. And we're going only to have something which is not smaller. Additionally, now let us handle the other thing. So if x star y star is known to be an equilibrium, then for any x, the first player benefits from x star y star at least as it benefits from x y star. By the definition of equilibrium, it implies that since it's for it implies that also the utility of the first player in x star y star is at least as its utility when we minimize over y over all y's. And if we look, since it's true for all the x's, we can also say that it's also greater or equal if we look at the maximum over x's. Because for each x, ui, the utility of the first player in x star y star was at least as the minimum over y's of its utility in xy. So we can also take the maximum of x's, and we are going to keep the inequality. So by now we have proven that the utility of the first player in x star y star is at most maxmin and at least maxmin of his utility, and therefore it's equal to its utility, maxmin. So it means that x star max minimizes player 1's utility, and analogously we can prove that y star max minimizes player 2's utility. Okay, that's one thing. So we've proven that both are max minimizers. Now, since the utility of the first player is C1 minus the utility of the second player by the definition of constant sum, we now can imply the lemma, and Cy minus U2 x star y star, which is equal to max min. The lemma implies it's equal to min max, so it's going to equal to min max of the utility of the first player. Because the best the second player can get for himself is the worst it can get for the first player. And then we have that the utility of the first player in the equilibrium is equal to min max, which is equal to max min. That's the second statement, and now we are going to prove the opposite. So we now assume that max min and min max give the same value, and that we have x star y star somewhere who are max minimizers for the corresponding players. So first of all, call that max min, which is equal to min max, v star, and the lemma implies that max min of u2 is equal to min max of u1, c minus min max of u1. So c minus v star, because we define v star like here. Now, since we assume that x star is a max minimizer for the first player, then we know that the utility of the first player when it uses x star and for any y is at least the maximum it can get for the concrete yes, so a max x star is assumed to be a max minimizer for player 1, which means that the utility of player 1 when it plays x star against some y is at least her utility when she plays the best possible thing against the worst possible thing, because we are not sure whether y is the worst possible, but it's true for everyone. Analogously, since y star is a max minimizer for player 2, then what she gets when she plays y star is at least c minus v star for any x, and that implies that u1, since u1 is in xy star is c minus u2 in xy star, then u1 is at most, we just reverse this inequality, is at most c minus v star. So u1 is at most v star. So we now have that u1 in x star y is at most v star, and u1 in x y star is at, excuse me, u1 in x star y is at least v star, and u1 in x y star is at most v star. So we can just, since it's true for all y and all x, we substitute x star instead of x, y star instead of y, and this, as a particular case, will give equality, will be a particular value in both of those inequalities. So the utility u1 of x star y star will be at least v star, and u1 of x star y star will be at most v star, and therefore it will be exactly equal to v star. Now, if deviating from x star in this profile, x star y star, could improve the utility of the first player, then because it's a constant sum game, it would decrease the utility of the second player. But that would contradict what we know, that the utility of the second player for any other x can only be at least c minus v star. That's what we proved here. And similarly, the deviating from y star cannot improve the utility of the second player, because again, for any y, if, let me think, because if we could improve the utility of the second player, it would be in a constant sum game, decrease the utility of the first player, contradictory to this statement, that the utility of the first player for any y with x star is at least v star. So x star y star is a Nash equilibrium. So basically we have proven that not only does being a Nash equilibrium imply that its constituent strategies are max minimizer and a minimizer, a max minimizer of one player and a max minimizer of the other player respectively. And not only does that imply that maximum of x minimum over y is exactly as minimum of y and then maximum of s, also the opposite holds. Now we are going to prove a very simple corollary. The first one is that we have exchangeability. So that if there are two profiles who are Nash equilibrium, then any strategy from any profile for the first player can be paired with any strategy for any profile of the second player, and that's still going to be a Nash equilibrium. And that exchangeability, that's a very important, rare, but if a zero-sum game it holds, that's a very important property. And another property, which is pretty much a reformulation of what we proved, is that a constant sum game has an equilibrium if and only if maxmin is equal to min max. So consider the exchangeability first to prove it. Assume that you have two equilibria, two Nash equilibria, x, y, and x prime, y prime. Now, by what we proved, the fact that x, y, and x, y, x prime, y prime are Nash equilibria implies that x's, the x and x prime are max minimizers for 1, and y and y prime are max minimizers for 2. And it also implies that max min of y1 is equal to min max. Now, but from what we proved in the other direction in the theorem, as long as we have this maximum of a minimum is equal to minimum or maximum, then any couple of max minimizers will give us a Nash equilibrium, and therefore x y prime, x prime y will also be Nash equilibria. Now the characterization is immediate in the sense that we remember that we proved that if we have an equilibrium, then maximum of a minimum is equal to minimum or maximum. Now, if maximum of a minimum is equal to minimum or maximum, then we can just take a max minimizer and for one player and a max minimizer for another player, and we are going to get an equilibrium. So that also holds in the other direction. And then we have this characterization. Now, since this max over minimum is equal to minimum over maximum, is something which characterizes Nash equilibria in a constant sum game. It's an interesting value, and we define this value as this utility, maximum of a minimum, or minimum of the maximum, as the value of the game. That somehow is an important value in the game. Okay, let us wrap up. So what we've done is we've defined what it means to have a constant sum game, and as I said, often people study zero-sum games. Let's say in Osborne and Rubinstein, they study zero-sum game. So you can just look at their proofs and get our proofs, or the other way around. We look at our proofs, substitute the constant 0 and get their proof. So it's important to know that what we do is true for constant sum games, for any constant, but the substantial difficulty is the same as for zero-sum games. We characterize the existence of Nash equilibria in those, and the Nash equilibria, how they look in those games. We in particular saw that all the Nash equilibria have the same utility and that we have this exchangeability. So a profile is a Nash equilibrium profile if and only if, well, if there is a Nash equilibrium, which you remember we characterize using that maximum of a minimum is equal to minimum of the maximum, then we simply need to take a max minimizer for each player, and we can pair them in any way. So that's what they call exchangeability. Okay, so that's what we have done, and please let me know if you have any questions.